Hey everybody, welcome to section 5.91, applications of exponential and natural logarithmic functions. Day 1, we'll just talk about the exponential. So this first example, it comes from population growth. And honestly, the number e, students ask me all the time, where does e come from? And I've got, I think if you look back in the notes, you'll see we talk a little bit about where e comes from, but honestly, the base e is used a ton in population growth. Anytime you're biologically something that's growing grows as a result of how big it is in the first place, and anytime that's happening, e lends itself very well to lots of different applications. So this is going to be when your textbook talks about exponential growth rate. This is consider this to be a vocabulary word. You might want to even circle it or highlight, as I have not actually done at the moment. But exponential growth rate is something to look for. It's a keyword. And so when you see that, it's k here, assuming you've got to assume that the base is e. So nowhere in the problem did they talk about e except when they give you 1.1%. That means this k has got to equal 1.1%, and you've got to use base e. So part A looks like this. You've got some knowns. The known, you know that k is 1.1%, and you've got to, don't forget to translate that to a decimal. P0 is 113.7 million. We'll do the whole problem in millions. So the input is in millions, the output will be in millions. And then you have to find, and then the unknown is t. So, and we'll say that t is just years since 2011 when the whole thing started, when you've got P0. Great. That's part A. Part B is to graph it, and you can see this is what it looks like. Notice that it's not exactly a square graph, and that's fine. Desmos is able to handle that, and you should be able to zoom in and out to things on your graph, on your on a graphing calculator if you have one. So I'd love to show you how to do that on Desmos or any calculator that you have. Part C is given the year 2015, that means that time is equal to 4. What's going to be the population? So if the input is 4, what's the output? You can just put it in right here, or put it into a table on Desmos, and then you get 118.8 million people. The doubling time is unknown, so that's what we want to find. What is the doubling time for all this? So you could, if you wanted to, calculate out P0 equals 113.7. You know that, so double that, you get to 227.4 million people. And you can plug that in here, but you notice that as a first step, you'd have to divide both sides by 113.7 in order to get to t. And that gives you 2. That's not a mistake. That you could start right here. 2 equals e to the 0.011t. This is a bit more concrete as a step to kind of like actually calculate things out, but you could, and sometimes you have to start right here. If you know the doubling time is 2, then you just say 2 equals this growth factor right here, e to the 0.011t. Anyway, recognizing that it's an exponential function, you can rewrite it as a logarithmic function, taking this log here, log of 2, and moving this over, and that's the power. Sorry, this is the exponent, and the power is 2, and the base is e. So then you have this, and then the last step is to divide both sides by 0.001, and you get this thing, which you can now plug into your calculator, and that's 63 years. And actually, nowhere in your calculator, like I said this before, nowhere in your calculations do you type into your calculator 113.7 or 227.4. What you type in is the fact that it gets doubled, and so 113.7 has absolutely no bearing on how long it takes to double. Your starting amount has absolutely no amount on how long it takes to double. It's only purely a function of the growth rate. Let's jump down to example 2. This is interest compounded continuously. So here's a formula if you want to talk about interest not compounded annually or monthly or daily, not getting interest every hour or every minute, but continually getting interest at every, not in chunks at all, but in a smooth curve, then this is the formula that you can use. So that's one more application of E. It allows you to compound things continuously. So they give you all these knowns. If you know the initial amount, P0, you know the final amount here, and you know that it took 5 years to get from 2,000 to 2,504 and 65 cents. So what you can do is you can plug all that into the formula, and what you don't know is the K, the interest rate. So divide both sides by 2,000, you get this, and then rewrite as a log, you get this. Remember that the exponent goes on out here, and the power goes inside the log. And of course it's a base E. So base E is a natural log here. So dividing both sides by 5, we finally get a fraction that you can type into a calculator to get K, which is 0.045, which is converting that to a percentage, that's 4.5%. So here at part B, they ask you, now that you know what the rate is, you can plug that into the formula and you can write it, you can express it as something that you'd be able to type into, say, Desmos or a calculator, and there it is. If the input is 10, then the output would be some number, and I want you to find out what it is. So go ahead and type it in. Make sure you know how to type it into either Desmos or a calculator and get the answer. And while you do that, I might as well just mention that the one thing that my kids order most frequently at restaurants is grilled cheese. You probably went through a grilled cheese phase too, you just don't remember. That's what they love to eat right now, and by the time you actually watch this video, they might be, I don't know, driving or going off to college. But at the moment, they love grilled cheese at restaurants that they had last night. Part D, what is the doubling time? So I've said it before, and I think most videos, but you can do this concretely. You can figure out that if you start at 2,000, then the final amount would be 4,000, because that's double. But it's an unnecessary step. You can plug those in here, 4,000 equals 2,000. But you notice the very first thing you do is divide both sides by 2,000. You get 2 here. That's the same as this 2. Doubling is over here. To multiply it by 2, to double your amount, you can put right over here as almost as P over P0. The fraction P over P0 is 2. So you'd put it right here. 2 equals e to the 0.045t. Rewriting it as logarithmic function, then you get this. And dividing both sides by 0.045, you get this, which you can plug into a calculator and get 15.4 years. A function only of the interest rate and not of the actual original amount. So yesterday we talked about exponential growth. P of some sort of time is equal to P0 e to the kt. But what I want to talk about today is exponential decay. And so the formulas are exactly almost identical, except you've got this negative right here. If you want to put a negative inside the function, that you already know that's going to be a horizontal dilation of -1. It's going to flip it horizontally about the y-axis. And that's exactly what you see here. There's exponential growth and exponential decay. This is populations growing, like we saw in the population of the country Mexico as a previous example. But any population that is growing without any kind of natural inhibitors or reasons why you should slow down, like viruses or shortage of food or plagues or whatever. This is how populations grow. But when you flip that around, exponential decay is like this. So if things are going to decrease by amount by 1/2, say over every certain amount of 5 years or 10 years or whatever, that's decay rate and half-life. And so we've got some formulas here. You might remember this. I think I gave this particular version of the format, like t equals natural log 2 for doubling over k. But notice that if you multiply both sides by k, you get this formula. You see that k times t is equal to a constant number. That's an inverse relationship. You can see here. So you could also divide both sides by t, and you get k equals natural log of 2 over t. So these 3 formulas are 3 versions of the same thing. You only really have to memorize one of them to get the others. These are the exact same formulas here. So if you have decay rate and half-life you use the exact same formulas, just with the understanding that when you use these K's and T's, well, you use the K value here, this formula would have to have a negative to flip it to make it decay. All right, that's enough talk about that. Let's do an actual example. Carbon dating, fascinating stuff. So this, we've got linen wrapped in the Dead Sea Scrolls. It's lost 22.3% of its carbon-14. We know that carbon-14 has a half-life of 5,750 years, meaning if you've got 10 grams of carbon-14, which is actually naturally occurring in the atmosphere, like carbon in CO2 has a certain amount of actually radioactive carbon. It's from sunlight. It's just part of the natural process. So, but as soon as you stop taking in new carbon dioxide, then you stop replacing your radioactive carbon, and then it starts decaying. So what you know is that the doubling rate, big T, is 5,750 years, and you lose, this is tricky, you lose 22.3%. So what you can't actually use that in a formula. You have to subtract from 100% to get how much has remained. 77.7% remained. And where do you plug that into a formula? It's actually the ratio P over P0. What you don't know is the time, the little time. You don't know is the rate. But we've got a formula for the rate. Don't you worry. We can take this 5,750 years, and we can plug that in for big T, the doubling time. K is equal to the natural log of 2 for doubling, or half-lifing, and then 5,750, and that's going to be the exponential decay rate is going to be about 0.00012. So we've got this formula here, and you can even rearrange it. P over P0 is going to be equal to this. And the way that we can finally plug in some actual numbers is we get this ratio, the amount that you used to have compared to the amount that you started out with. Sorry, the amount you started out with, the original amount, with the amount that you actually have now, is 0.777%. 77.7%, or just 0.777. And that's equal to negative from the formula, because this negative indicates that it's decaying, not growing. This is the K value that we calculated, and the base is E. Finally, so now we can rearrange this so that the exponent goes over here and the power goes over here, and it's a log. Dividing both sides by this, we get 2,103 years, which tells you how old the Dead Sea Scrolls were. If you don't know what the Dead Sea Scrolls are, Google it, watch a YouTube video on it. Most amazing, by and far the greatest archaeological find of the 20th century. Easy. Blows everything else out of the water. Fascinating story. I highly recommend you check up on it. Example 3. Population growth. The population of Kenya is now doubling every 28.2 years. This is back in 2011. So it's just one more application of the formula. So what is the exponential growth rate? It's 2.46. That's a K value. And you can just use this formula here.